Hello everyone and welcome back to Newegg TV. My name is Paul and JJ's back. He came back because, well, he cares, of course. We spent a long day shooting a bunch of stuff a couple days ago and it got a little late. Well, mostly me. I was kind of going a little crazy there towards the end. So if you watch our triple SLI demonstration of the GTX 660 Ti, my apologies. Anyway, this video is a little bit more straightforward, but essentially what we're talking about here is the ASUS incarnation of the NVIDIA GeForce GTX 660 Ti, the DirectCU II version. So we're going to talk about what goes into a custom-built card, because whenever a new video card is released, such as the 660 Ti, there's typically a reference version that's designed by the GPU manufacturer.
Correct.
And then a lot of independent vendors, such as ASUS, will take that, sort of use it as a starting off point, build it out from there, see what they can do to improve it. And the DirectCU II cards have really done a great job at both improving thermals, noise generation, and just giving you overall a better card. But it's not just the cooler.
Yes.
There's some other elements too, and you can't really see those all the time without disassembling the card. So we have a reference card here. We went ahead and disassembled beforehand because it's a little bit more difficult to get these apart than the ASUS version. And we're just going to sort of go through it, say, here's how NVIDIA designed it. Here's what ASUS has done to improve that, and then we also have a little test bed set up. We're going to do some basic comparisons to see what kind of temperature differences.
You pretty much nailed it on the head there. You know, for us, the main focus is always trying to bring the best class of implementation that we can to whatever product that we're trying to implement, whether that's going to be like a motherboard, a graphics card, a networking product, whatever it might be. That's what we're trying to do in terms of looking at the complete design philosophy, whether that's going to be the componentry that's being utilized, whether it's going to be the firmware that's going to be going into it, like the VBIOS tuning, whether it's going to be the software that interfaces with the hardware. All those things have to be taken into consideration. And like you said, NVIDIA, as let's say a developer for the GPU platform, definitely takes a huge amount of care in going through developing a really solid reference series product. But there are definitely different GPUs that come out at different times where when we have enough visibility, NVIDIA can provide to us essentially the foundational information on the GPU design, and we can either utilize that and produce a reference design, or we can entirely essentially scrap that and produce our own PCB, produce our own VRM design, produce our own heatsink and fan assembly, essentially having a full, complete non-reference solution. And that's important to keep in mind because, as you noted, sometimes without taking a look at the card in itself, you might not fully realize the difference when you're looking at a card. There are even some cards out there where you can have a non-reference heatsink, but it can still actually be the full reference PCB VRM. So the under the hood componentry is essentially the same exact thing as what you would have in a reference card design.
Now, when you mentioned the term, I know there's a lot of terms out here since we're getting into a level of the card detail that a lot of folks don't see. So when you say VBIOS,
yes,
that is essentially, would that be the equivalent of a BIOS on a motherboard as to the video card?
Yeah, it's just like, you know, on the current generation motherboards, you have that UEFI, or some people still calling it the BIOS. It's the same thing. It's the operating firmware for the card, dictates how the fan curve might respond, which is important because you want your card to be well cooled, but you want it to be quiet. It's also going to handle voltage policies. It's going to give you the ranges for frequency adjustment. It handles pretty much the overall operating functionality of the card, and that can also be tuned by the vendor to be able to allow for maybe more flexibility or better performance. And performance not necessarily just related to, let's say, clock speed, but it could also relate to thermal performance or like the acoustic characteristics of the card. But the biggest thing, I think, more so that we just want to help users understand out there, that when we're going to be doing this comparison, it's about helping you understand the differential that comes into the design aspect of the card, because the reference card has to be designed from the perspective of meeting kind of a couple of different criteria, and part of that honestly is BOM costs, which is bill of material costs. So that means they are going to come in maybe cut down on some of the elements of the card that wouldn't. It doesn't mean that you're getting, like, let's say, an inferior product. It's just not necessarily as high end of a product that you could have in terms of the components that are being utilized. Because we're also in the situation that are sometimes we will produce a reference card at launch, and then after that fact, we'll take all the design information that we have and then produce a full non-reference. So it just kind of depends on what GPU and the life cycle that it's in terms of what we can do, whether it's something that we're launching right off the bat at launch, or something that's going to come after the fact. And as you pointed out with our GTX 660 Ti cards, all three of the versions that we have to offer, the standard, the OC, and the top, they're all full 100% non-reference, and they've launched that way, so we don't have any reference cards.
All right, so shall we start off with a comparison?
Yeah, let's take a look here at, I guess, the reference card. You've got it here, and it's pretty straightforward. This is using what's referred to as a blower-type design, which does have a benefit of helping to additionally dissipate some additional air outside of the chassis. But for a lower TDP card, actually like a GeForce GTX 660 Ti, which is targeted about 150 TDP in terms of the wattage, it's actually not that really big of a difference between an impeller solution versus a blower-based design. And it's also important to take consideration that even though you might be exhausting some of the air out, because of the increase in the temperature on the PCB board itself, you can actually be creating hot spotting in certain areas of the card, such as on the back of the PCB and even to this whole shroud in itself. So you can actually have pockets of hot air that wouldn't normally exist on, let's say, like a non-reference product. So there are sometimes users that have a misconception that one is better than another. The reality is, regardless, as long as you have good quality airflow within your system, the overall temperature performance you're going to have from either one would generally be won by the non-reference card in terms of overall total temperature performance for that card. And in terms of the difference in ambient temperature performance, it's pretty much going to be nil. And in, like I said, some situations you might have even slightly reduced hot spotting on this type of design versus a blower type design.
Now, I've seen several of these 660 Ti's as well as other series of video cards come out, and the shroud cooling design, I always sort of hear back and forth about that. A lot of times people will say the open design of the cooler ejects more hot air into the case. It's going to raise the ambient air, temperature in the case versus the shroud, which is going to essentially minimize the airflow that goes into your case and primarily ejected out the back. In your testing, what sort of temperature differences have you noticed in the other hardware in the case when you're using an open design versus a enclosed design?
Like I said, that really varies, and it comes down to just airflow. I mean, we've done internal testing with about 20 different types of chassis, and in some situations we find that one card might give you maybe a +1 or 2 C ambient. In other configurations, it could be the other card is winning out, but it also comes down to localization. Like I said, sometimes those hotspot characteristics. So realistically, honestly, especially for what 90% of the market is doing with one single GPU, you're going to get an overall generally cooler system in total when running a non-reference type design card than you would be doing with a reference card design. And it's also very important to consider that the maximum amount of heat that's being expelled is exponentially lower than a much higher TDP target card. So like if you were talking about like a 690 or a 680, but 680s are actually very power efficient as well. It's not like what you were taking a look at a couple of years ago where the power efficiency of cards weren't as good as they are. So therefore the amount of heat that's having to consistently be dissipated and maybe being recirculated back into the case could be much higher than what it is what you're dealing with now.
Okay, so now let's just finish off talking about the cooler before we go into the PCB elements. Here are the other components of the cooler that have been disassembled. So you have a VRM cooler right there, and
which is nice. It's definitely a lot of non-reference cards don't. A lot of reference cards don't usually take the effort into putting in an actual VRM heatsink. So that's good to see because we also do have a VRM heatsink on our card, and historically non-reference cards that's been an area where they've excelled at.
And apart from the GPU, that is one of the hottest parts of the card.
It is actually, yeah. The MOSFET area, we are definitely going to be utilizing much higher grade MOSFETs, which we'll talk about when we make these comparisons here. But it's still good regardless to know that the hottest portion of the VRM is being added in terms of dissipation by that.
And then apart from that, we also have a aluminum fin assembly right here. It does have a copper base on there. That is just a sort of a comparison here between the reference design and then you guys have direct copper heat pipes that make contact there. So this is a fairly effective cooler, but you can see it's got some padding here where the shroud would actually make contact with it.
Yeah, and that's also helped to minimize a little bit of the sound footprint of the card. But as I'm sure you've been able to hear in your testing of this card as well as other similar reference cards, one big difference between our two solutions is that our card operates essentially at almost an inaudible footprint under full gaming load as well as being idle, while this card, even actually when idle, it still was producing a bit of a hum. I wouldn't say loud by any stretch of the imagination, and definitely under gaming load, it was still not loud, but it was clearly audible compared to our solution. So that's also showing you that in terms of the differential at that temperature performance and the way that this is designed, there is going to be an acoustical differentiation between the two design implementations, because total temperature performance, you know, this card generally idles somewhere between about, I'd say 35 to about 37 C. Definitely not bad, but our card is usually going to be idling somewhere closer to about 29 to about 31 C. So that's quite a bit of a drop off. And in terms of total dB differential, it's about a 9 dB differential between gaming load on the two cards.
So definitely a much quieter implementation.
Yeah, quieter and cooler, which is definitely our goal. So when taking a look here at the rest of the card, you can see that you've got a lot going on. For some of you guys, you might not know what all this power componentry is here, but this is really the big section that carries a lot of differential in terms of the product design. So that's the actual voltage regulation componentry for the graphics card. So in this area, we have what are called our MOSFETs and our drivers. Here we have a 4-phase power solution. As you can see, we have 4 inductors or 4 chokes. And then we have, you know, some standard, at least solid capacitors. That definitely not bad. But you can also see that here in this back area, there are some spacing for some pause cap implementations for some additional power delivery. But they haven't been utilized. They haven't been implemented there, which that's also going to be one of the differences in the characteristics when we start touching on aspects of our card as opposed to the, let's say, this reference design card. Now, in terms of the total card consideration, there are some other aspects here that we're going to take a look at on the back of the card. And NVIDIA has actually been very aggressive at trying to maintain a good overclocking experience on their reference series products. And as such, they've continued to actually kind of take some of the stuff that we have historically done as a non-reference vendor and implement them on reference designs and recommend them. So you can actually see a back-to-back GPU design, which you've been very conscious of as we've talked about a lot of our cards over the years. You can see that they're actually doing the same type of implementation. They do have actually 2 pause caps that are on here that aid a little bit in additional overclocking support. So as we overclock the card and you're taking advantage of that GPU boost technology, there's additional power there to be able to supplant that overclock frequency and hopefully be able to stabilize it a little bit. So definitely a solid card, but when we're going to take a look at the total class of performance that we're going to have between the two cards, we'll see where we're going to be able to provide an advantage.
And just for folks who maybe aren't familiar with the electrical components, pause caps right here, it's a different kind of capacitor. It's we don't want to get too into detail there, but the positioning, having them here directly behind the GPU.
That's the important part, exactly, is that it's all about efficiency. So of course, the further away they were from the GPU, the less efficient they're going to be being able to provide power to the back. And we've usually referred to that as a back-to-back type design. So you, of course, directly on the other side, we have the GPU, so you can see that you're getting that best power delivery. And in our solution, we're just having to use even more pause caps to be able to give you even greater overclockability, assuming that margin is present within that GPU.
All right. Anything else to note here on the reference board before we move on to the DirectCU II?
The last part is what you touched on a little bit. We actually had to do the disassembly off camera, where we're going to do the disassembly on our card pretty much live. The predominant reason being is that I think there was a total maybe about 12 screws that we had to take off with different sizes, different threading. You know, and so for you guys that kind of want to intermittently take apart your card, maybe clean it, maybe apply different thermal compound, it's going to be a little bit more definitely time and effort. Where on our card, you're going to see it's pretty much just 4 screws. So it's a far simpler process to be able to do that.
All right. So I think in order to disassemble your card, well, we're currently using it.
Yep. So let's go ahead and exit out of this.
We've been running the Unigine Heaven 3.0 demo.
But I think right before we cut off the card, we can take a look a little bit about the performance characteristics that we've been talking about here.
Okay.
So you can see right here, we've actually got 2 log files that we've loaded up that are running from the GPU tweak software that we have running on both the reference card as well as our non-reference card. And so this is allowing us to track information per 1-second intervals relating to the clock speed, to the temperature, and to the power target aspects of the card. So overall, it helps us to kind of really see the differential in terms of how the reference design is going to be comparing against the non-reference design. So we can see on this side, on our left-hand side, we've got the actual GPU boost frequency, which is a bit more varied. Overall, it's reaching effectively the same maximum boost clock, which is about 1058, but we can see that it's kind of floating a little bit more in and out. Actually, and on our card, we can actually see that it's much more consistent at actually 1058. But when you take a look at the whole picture, there's actually more to this. So if we go ahead and scroll all the way down here, we can actually see that here's actually our power target values. And we can see that our card is effectively only hitting not even really consistently 90% in terms of the power target. So that means we've got quite a bit quite a bit of additional room. Now, power target is defined by power consumption as well as temperature and other factors on the VRM. And it's important in terms of the total dynamic clocking ability of the card and the overclock ability of the card. The closer your card is effectively to a maximum power target means that effectively you're capping the GPU boost clock frequency. Since these graphics cards have a set core clock, and all overclocking has to be done through the GPU boost itself, it's important to try to have additional flexibility in either being able to define a power target over 100% or already being underneath 100% so that you have greater overclockability on your graphics card. So if we take a look here at our reference card, we can go ahead and move all the way down here, and we can take a look at the power target values.
So you're getting about 10% below on the DirectCU II version, whereas with the reference card, you're hitting almost 100%.
Correct.
Most of the time.
So you can see that in terms of total margin, even though the reference card will allow us to go ahead and still define a power target over that, still collectively in terms of the total range that we're going to have available on the card, it's going to be lower. So that's helping to show that we are definitely putting that time and effort in terms of the total design to give you the best flexibility and the most range available to you on the card. And as we go ahead and we move all the way over here, if we take a look at temperatures as well, you're going to see that definitely, I wouldn't say a hot card. I mean, 75C is definitely not by any stretch of the imagination hot, but it is going to be hotter than what our card was running at, which you can see was closer to about 69 or 68. And the other great thing about our card is that that's going to be a much more consistent temperature even as you overclock it. So as we maybe go in and set it to higher clock speeds, we're actually going to have a pretty similar temperature, usually about maybe I'd say a 1 to 2C swing, maybe 3C if you're getting over 1135 in terms of the boost clock, which would be giving you a pretty actual high core clock, which keep in mind that right now we're only at 980 with that effective GPU boost giving us about 1058, while with the reference series card, this temperature would actually be getting probably over 80C as you start to overclock the card even further.
And that simply comes down to the quality of the components that you've used, the way that you've set up the the way you've made your own custom design as compared to the reference board, and that gives you that extra headroom with the power target?
That's correct. So all those considerations come into play, and definitely the high performance DC2 design in terms of that direct contact copper, and then of course with the additional airflow where we're exponentially having a much higher level of airflow in the card, but having that curve in terms of our fan curve is still really tuned well so that you're not essentially hearing the card even at those higher clock speeds. But with that, let's go ahead and actually take the card off and quickly take a look at the power componentry differential between the two.
Sounds good.
Okay, so here you can see we've got the graphics card. There's just 4 screws right here, so we're just going to go ahead and unscrew these guys. And we're going to go ahead and take a look at the inside. Now we can already see that right here, right off the bat, you can see compared to the actual reference card, we have 4 pause caps versus the 2 pause caps. In total, we actually have a total of 9 pause caps on our card versus the reference, which only has 3. So there's quite a bit more in terms of the total componentry that we're using versus what the reference card would be utilizing. Another nice design touch that we have compared to the reference is actually going to just be a nice kind of diagnostic or troubleshooting feature that for users when they're actually going about connecting the card, we actually have diagnostic LEDs here on the back, so that if you go ahead and have the correct connections and everything's working correctly, you're going to go ahead and have a green LED light up for these two, but maybe you don't have it physically connected, maybe you forgot to actually make one plug connection, it will actually light up red. So it's a nice little visual indicator to let you know whether you've got things set up correctly.
I find, especially since I switch between video cards a lot with doing testing, it's really easy just to accidentally forget to plug in PCI Express power, and those little LEDs always give me a nice immediate indicator that, hey, you forgot to plug that in.
Okay, so we can see right here we've actually got the 2 portions, and we can see on this side we've got the very high performance DirectCU II heatsink and fan assembly with the 3 heat pipes. This portion is of course all nickel plated, along with this nickel plated to minimize oxidation, and even you'll see actually on some non-reference series cards from other companies they're not taking the extra cost to go ahead and do that nickel plating. So it's even in solutions that have similar heat pipe technology, it's not necessarily going to be the same. And of course we've got this nice high quality finned mass assembly to go ahead and aid in that overall dissipation ability. Now when taking a look here, at the card, we can see that it definitely, I think, looks overall actually just better looking for one, and that's showing that kind of design attention to detail. And we can see that we've got a really nice matte black PCB here, but of course what we're looking at that's going to be really different is going to be the VRM assembly. So here we of course have the VRM heatsink that covers our high performance super alloy MOSFETs, which allow for actually higher voltage levels and run at a lower operating temperature than the normal MOSFETs that are utilized on reference series components. And right next to that, we can of course see the additional phases in comparison to what we would have on the reference design. So we've got 1, 2, 3, 4, 5, 6, and you can see actually they got that really cool SAP logo there to let you know those are those alloy-based chokes, which not only provide better efficiency, better performance, and better power output delivery, but also help to minimize on what's sometimes referred to as choke whine, or let's say choke hum, which is sometimes audible on some of the reference series cards which don't use these higher performance chokes.
And one thing I like about the two-fan cooling assembly as well as the open fins that you have right below that is when this is sitting above all that power delivery, the fan is pushing air across those fins and almost getting direct airflow, fresh air going at those versus the air that's being pushed from the blower
hot
fan
air.
across the GPU first.
Because you're actually blowing, you're 100% correct, and that's a great point that I was actually going to touch on, is that with the blower type design, the GPU is at its hottest point, and you're pushing through air that's already at its hottest point and then being expelled directly over the hottest area of the card. While here, we're able to aid in that process by giving actually more ventilated air and helping to reduce this componentry, which is already running cooler than the reference series components would be. We then, of course, meet that kind of trifecta of the super alloyed power design, where we have the chokes, the capacitors, and then the MOSFETs with our super alloyed capacitors. Now, right behind those, you can see right there, we've got those additional pause caps, so those really high performance capacitors, which work in conjunction with our alloy-based capacitors here, at giving us even better overclockability, better stability, and overall better performance. And they help to minimize noise, especially at high overclockability levels, which is important for a card that's dynamically clocking back and forth. And going along with that, right down below there, we've got the DigiPlus actually Pwm controller itself, whereas compared to the reference design, it's still using an analog controller. And so this is just going to allow us to have better efficiency and overall better performance from our VRM design. So collectively, that's kind of helping you to see the design differential when you're talking about a non-reference card versus the reference card. And collectively, of course, even the PCB is going to be much larger versus kind of the little short PCB that you have here on the reference series cards.
The digital power delivery, because I know you guys implemented that across your line of motherboards, and it's met with great success. As far as providing power to the GPU, is that just like with your motherboards, is that providing like faster power delivery, like as it's switching between power states, going from 2D to 3D?
It helps to actually minimize an effect that's called ripple and overall noise. So it's just a more efficient controller at being able to manage how the VRM actually operates, as well as also giving you more accurate and precise control when adjustments are being made to, let's say, like our GPU tweak software. So the analog solution definitely isn't a bad solution. I mean, we've used analog solutions on previous generations graphics cards like our GTX 580 DirectCU II, which is a beast of an overclocker. So it's not to say that an analog solution is going to be automatically inferior, but when it comes to the best performance, especially for dynamically clocking platforms, just like our motherboards when we adopted it, that were dynamically clocking because of turbo on CPUs, take for instance, it's just a more modern and the best approach that you can bring to power delivery solutions right now. So that overall gives a bit of perspective on how there's a difference between the reference series cards and the non-reference series cards.
And that's going to wrap it up for this video. I'd like to thank JJ for coming back and sharing some more information with us. Again, this has been the ASUS GeForce GTX 660 Ti DirectCU II. It's also available in a OC and a top version, which are manufacturer overclocked straight from ASUS. And when you guys do your overclock versions, you bin the graphics, the GPUs, right? And they essentially separate from the standard models, which can easily hit, the boost clocks and everything, to the top series, which is really the GPUs you guys find can actually perform significantly better?
Yeah, I mean, it's two factors. We definitely bin the GPU to be able to ensure that it runs correctly at that speed, and we try to pick a frequency that tends to have more a larger level of separation that maybe less of the actual standard series would be able to actually achieve, but definitely you still have great overclockability within the standard and the OC SKUs, but with the top you're going to have bin level performance to not only be able to ensure that you're running at that speed, but of course hopefully have some additional headroom so that you can overclock higher.
All right. Well, those 3 models, all available from ASUS. The 660 Ti has been doing great so far. I'd like to thank JJ for coming back because we spent so much time already a couple days ago, and he's like, I want to come back for more. So we said, sure, JJ. We always like to have you here. Thanks a lot for watching, everyone. If you want to see more of our videos, you can check out youtube.com/Newegg. If you want to see more of JJ, you can check out the ASUS ROG YouTube channel. And we'll see you all next time on Newegg TV.